So we're now going to talk about some of the overflow strategies that are provided with Project Reactor's Flux. And as you can see, there are 5 of them. These, again, are for non-back pressure aware publishers and subscribers. The publisher just slams the data out as fast as it can, and the subscribers deal with it in the way we're about to talk about. So this is necessary when a subscriber can't keep up with the rate at which the publisher is sending the data, but the publisher is not aware of the fact that there's back pressure, so it just blindly generates data as quickly as it possibly can. So let's talk about these different approaches. This one says, the buffer says, as the name suggests, all the values that come down from the publisher are buffered so that the subscriber will eventually get around to processing them. And buffering just means it puts them into some invisible queue that you don't see when you write the code, but it's lurking under the hood in the implementation, and so you have to be prepared for things to buffer. The problem with buffering, of course, is, as we said, if you have chronically hyperactive publishers, they will eventually overwhelm the memory resources on the subscriber, and then you'll get out-of-memory exceptions, which are really bad because it's very hard to recover from them. Another approach, another strategy, is to drop the most recent value if the subscriber can't keep up with the rate at which things are coming in. So it just says, hey, something comes in, my buffer is full, or I can't deal with it anymore. Let's drop it on the floor at that point, the most recent one. The error strategy says throw the overflow exception if the downstream can't keep up due to slowness. And this says illegal state exception, but I think in my experience, it's actually the overflow exception. I'll have to go back and double check that, which would be a better exception to throw than illegal state exception. That doesn't really make a whole lot of sense. And then this one says there's no buffering or dropping, so subscribers must handle overflow or they will receive an error. This, like I said, this is a really mysterious strategy, and even searching around with ChatGPT really didn't provide much light on what this is supposed to do. We'll take a look at an example later in the course. We'll get to see what it does, but it's not very well documented at all. And then finally, the last policy here, last strategy says only keep the latest on next value. So in other words, unlike drop, which says drop the latest value, latest says only keep the latest value. And so what it's really doing is as values come in, they have a buffer with size 1, and they put the latest value in there. And so that's the one that will be set up, and it just overwrites whatever was there before. So those are the 5 strategies. There's a way to provide these strategies using the 2-parameter version of the create factor method. We'll talk about different ways to make fluxes later, but one of the ways is using something called create, in which case you give it an emitter, we'll talk about that, and you can give it an overflow strategy, which is the back pressure strategy or policy for that particular instance of the flux that's created. This, by the way, is a fun example of a very complicated marble diagram, which looks like a little kid got access to a spirograph. You probably don't remember spirographs, but they were toys that we had when we were kids to draw little circles and stuff. And this is a little bit more harder to understand what the heck it means, but if you read the description and you think about what it does, it sort of documents how this works. You can specify the overflow mode to apply if the subscriber can't keep up with the publisher. So here's an example where we're going to make ourselves an emitter that'll generate a whole bunch of values at supersonic rates. And we're going to say the overflow strategy is to throw this exception if the publisher can't keep up with what's being generated by if the subscriber can't keep up with what's being generated by the publisher. How could that happen, you might ask? Well, as you can see here, we're going to use the parallel scheduler. So we're going to have whatever the emitter is, it's going to run in one thread or one pool of threads, and then the subscriber is going to run in a different pool of threads. And maybe it can keep up, maybe it can't, depending on a bunch of different factors. So we make the emitter to generate a stream of random big fraction objects that'll come zipping out as quickly as they can be generated. And then we say, hey, if we can't keep up, throw this error. Maybe not the best strategy to have, but that's what it's going to do because that's what we designated it to do. This operator, the one that we just looked at, the two-parameter version of create, this one here, is different from the one-parameter version. And what happens with the one-parameter version of create is it just buffers everything and doesn't support any other back pressure strategy. So this one is capable of running out of memory. So be careful when you use this that you don't have publishers that generate data faster than subscribers can keep up. There are also a whole slew of other operators that allow you to control the back pressure. There are these things called on back pressure star, because there's a bunch of different ones. And we'll talk about some of the different ones. We have on back pressure drop, on back pressure latest, on back pressure buffer, et cetera, et cetera, et cetera. So here's a simple example. This is on back pressure drop, which says ignore things that can't be processed until it's possible to process stuff like the burst debates. So here we're going to have a bunch of mouse moves that are generated, and we're going to subscribe to run these things, and we're going to do some computation with the mouse moves that come in, and we're just going to drop the events if we can't keep up. Here's another one. This is on back pressure latest. This is kind of similar. We have mouse clicks this time, and we're just going to keep the latest version of events if we can't keep up with them. And then here, similar thing, we're going to generate a whole slew of values from 1 to 1,000,000, and we're going to buffer them. And if for some reason we can't keep up, we're going to drop the oldest. So you can see sort of buffer things and also indicate what to happen if you can't keep up with the rate at which things are occurring. This stuff is very important in some contexts, not important at all in others. The key point here is that if your producers and consumers, your publishers and subscribers generate things at rates that are incompatible, these strategies might be helpful. Honestly, a better approach is usually to use back pressure aware producers and consumers or publishers and subscribers, and then a lot of these issues disappear. So that's the end of the overview of the Flux Overflow strategies. We will come back later and look at some case studies that will walk through these things, and you get to see how they perform in practice.